Hello everyone, welcome to Pre-Algebra with Miss Betsy. Today we're going to be working more on solving word problems, specifically motion problems. These are the ones where we use the distance formula, which is distance is equal to rate times time. And we use those when we're calculating how far you travel in a given amount of time, when you calculate how fast you're going, when you can say if John leaves Albuquerque at 2 o'clock and Sally leaves Las Vegas at 3 o'clock. They're traveling different speeds, they're headed towards each other. How long is it going to be until they meet up with each other? These are the types of problems that we're going to be working with. For those of you who are tracking along with the book that I'm using Pre-Algebra for Christian Schools, published by Bob Jones University Press. This is the first edition. You can find where we are in section 4.9. It's page 163. If you're using another text, it makes no difference. These are just distance problems, and you can learn just as easily from here as you would from your own text. Now, our lame joke for the day before we get started is, imagine that there is a rooster on the top of the barn and he lays an egg. Now, is that egg going to roll off the top of the barn on the north side or on the south side? Let's think about that for a minute. Which way would that egg be most likely to roll? Okay, for all of you city folk out there, the rooster is the male, so of course he's not going to lay an egg to roll. And if you were going to ask a question that says, what time does the rooster crow? Well, I'm here to tell you from personal experience that a rooster crows anytime he feels like. It's not just at dawn. It can be at midnight. It can be at 3 o'clock in the morning. It can be at the middle of the afternoon. So roosters don't lay eggs, and they crow anytime they feel like it. So let's go ahead and get started. They have an example of a problem here that I want to just go ahead and read to you. A jet leaves O'Hare Airport in Chicago at 7 a.m. and flies south towards Atlanta, which is 606 air miles away, at an average rate of 420 miles an hour. An hour later, a jet leaves Atlanta and flies towards Chicago at an average rate of 500 miles an hour. Due to an error in calculations, the jets are flying at the same altitude and on the same route toward one another. How much time do the air traffic controllers have to change the direction or altitude of the jets before they collide? So it's a real life problem. Fortunately, things like that very rarely happen, but these are distance problems. If you're going in this particular distance at this particular rate, and if you keep on that same path, there's going to be an accident. So what do we have to do to make sure that you move out of the way? For our practical purposes, since I don't personally know any air traffic controllers, something that shows up is, like I said earlier, let's go ahead and meet in long view. You leave at this time, I'll leave at this time, and we'll end up at the same space. So that's balancing our rates of travel. There's a formula that you will use constantly. Some of you already know it, some of you don't. And you're going to learn it right now. It's D is equal to R times T, where D is distance, R is the rate, or the speed, and T is the time. This is the distance formula, and you can calculate the distance that you've traveled by multiplying together the rate, typically in miles per hour, and the time at which you have been traveling. So let's say that we have this question here. It says, how far will a car travel if it goes 50 miles for 3 hours? Well, what is it asking us? It's asking us, how far does it travel? Well, is that distance or rate or time? Well, it's distance. So how far will the car travel if it goes 50 miles an hour for 3 hours? Okay, now we could actually write this more technically correct, where we're showing how we can cancel the units. so that we would end up with only a certain amount of miles, but I'm not going to focus on units now. Just want to see the distance. 50 miles an we're traveling at a rate of 50 miles an hour for 3 hours. The distance that we have traveled in that 3 hours is 150 miles. It's not 150 miles an hour because that's the speed. The distance is 150 miles. Now the next question, next example here says, how far will a car travel if it goes 50 miles an hour for X hours? Well, let's look at that. 50 miles an hour for X hours. How far will it travel? That's the distance. How far will it travel if it goes 50 miles an hour for X hours? How far will it travel? We don't know how long it's been traveling, we just know that that's our unknown. How far does it travel? 50x miles. How far does it travel in 1 hour? 50 miles. In 2 hours, 2 times 50 is 100. In 10 hours, 500 miles. So this is an illustration of how we can use that variable. Now, what if it's asking us a question about the rate? How fast is a car traveling if over a time of 5 hours it has traveled 25 miles? What's our distance formula? Distance is equal to rate times time. And we want to know how fast the car is traveling. Well, is the speed that it's traveling, is that distance? Or is it rate? Or is it time? What's the rate? The speed at which you travel is the rate. So we're actually going to solve for this r here. Our problem tells us that we've traveled 225 miles. So we have 225 is equal to r times, now how long have we traveled? It says 5 hours. So we just simply substitute in the 5 for our variable t. What are we trying to find out? We're trying to find out the rate. That means that we want to isolate this variable here all by itself. How do we do that? Well, the rate has been multiplied by 5, so we're going to divide by 5. Inverse operation, do the same thing to both sides of the equation. You keep your equation in balance. 225 divided by 5 is 45. Show your little scratch work out here to the side if you're not sure about that. Divide by 5. 4 times 5 are 20. 5 times 5 is 25. So we have 45 is equal to r. So the rate at which this guy is traveling, what is it, 45 hours? 45 seconds? 45 miles? No, it's 45 miles per hour. Remember, the rate is the speed at which you travel. So it's problems like this that we're going to be solving in section 4.9. So if you want to look at page 164, they have one more very, very simple illustration of just what it's like to use variables. And it says, Jim rides his bicycle, or Miss Betsy rides her bicycle, at a rate of 8 miles an hour for t hours. How far does he ride? Well, what are we finding? We want to find how far he rides. So let's say, let d equal how far, I'm going to put how far Miss Betsy rides. And for what it's worth, 8 miles an hour is like a really slow speed. That's a very leisurely get out and just sort of pedal around a little bit and visit with your friend. So the distance that I ride is going to be my rate, which is 8 miles an hour, and I'm going to travel t hours. So the distance that I ride is 8 times t miles. And that probably seems a little bit strange to you because you don't think of 8t as being a description. But what this really is the recipe that says as long as I'm cranking out consistently 8 miles an hour, you can figure out how far I've gone. Like in an hour I've gone 8 miles, 2 hours I've gone 16 miles, 2.5 hours I've gone 20 miles. So we're going to use this whole concept of using a variable to help us solve these distance problems that we're going to begin right now. And we have our first big jump into a distance problem right now. Let me read this to you. It says, the junior and senior high Sunday school classes are going on a hike. The junior class leaves the church and travels east at 3 miles an hour. The high school class leaves an hour later, traveling at 5 miles per hour on the same route. How much time will pass before the senior high class catches up with the junior high class? And your brain was probably saying overload, overload, overload long before I got finished reading that problem. So when you're working with these word problems, don't let just the sheer volume of words in there psych you out. Just take it, break it up into little pieces, read it carefully, and first figure out exactly what they're asking you for. We want to find out the main unknown. What's the main question that they're asking you? So if we read in here, how much time will pass before the senior high class catches up with the junior high class? And let's think about that. If the junior high class leaves ahead of the senior high class leaves from church, and they hike, and they're going to catch up with the junior high class. So that's a total amount of time, isn't it, that the senior high class travels. So let's say that x equal the amount of time that the senior class hikes. And a lot of the time with these distance problems, it helps to draw a little sketch. So let me go ahead and do this little sketch. And I think I'm going to actually do it the way that we show here in the book first. And I'm going to come at it from a totally different way to interpret it. And you'll see that we have a good example of why it really doesn't matter how you set up. Of course it matters how you set up your problems, but sometimes there's more than one way that you can set up a problem and have it be correct. And I've addressed this in class, that when you're looking at your solutions, it can be legitimately correct, even if you have not followed the exact steps that you have in your book, because there are different ways that are equally legitimate to approach a problem. If you get stuck with something like that, just send me a text and I'll work with you. But first, let's go ahead and do my little picture here. I've already shown to you guys more than once that there is a reason that I do not teach art. But I think with that little cross on the top, we can say right there is the church. So the amount of time the senior class hikes. So let's say senior class starts here at church, and this is when they finish. So we have the senior class. And this is going to be x. This is the amount of time that the senior class hikes. Now if we have them, we also have the amount of time that the junior class hikes. Now let's go back and look in our book and see what it says about how long they've hiked. It says, the junior high class leaves the church, travels east at 3 miles an hour. The high school class leaves an hour later. So the senior high class has already been hiking, haven't they? So at the time the senior high class leaves, junior high class is already out here. They have this extra amount of time that they have been traveling. So if they've already been traveling 1 hour, then the amount of time that they have traveled is going to be the amount of time that the senior class travels plus that additional 1 hour. Okay? Do you see how we have set up the unknowns here, defining how long each class has traveled? This is very, very important that you see where we got the x plus 1. Junior high class went an hour more, so if you take the amount of time that the senior high class had been traveling, had been hiking, they hiked for 4 hours. The junior high class began an hour earlier, so clearly the junior high class hiked 5 hours. Sometimes just messes with your mind a little bit when you're using variables. Now, the next part of solving this problem, you've read it, you've drawn a picture, we need to plan a strategy. How are we going to figure this out? Now, distance problems are ones that lend themselves perfectly to tables. So let's say that we have the junior high class, we have the senior class. And we know what our formula is. Our formula that we're using is distance is equal to rate times time. But I'm going to put rate times time is equal to distance. And you know that you can legitimately do this because when you have something that's balanced, it doesn't matter which direction you have it. These are equivalent. Distance is rate times time. Flip it, rate times time is also equal to distance. Now let's look and see what pieces of information we can fill in here. For the junior high class, our book tells us that they're hiking at a rate of 3 miles an hour. How long have they been hiking? Well, we used our picture up here to see that the amount of time they've been hiking is indicated by the expression x plus 1. You read through your problem again, you say that the senior high class hikes at a rate of 5 miles an hour. And how long do they hike? We defined our problem to say let x equal the amount of time the senior high class hikes. So their time is simply x. Now, we have 2 blocks left here to fill in. How are we going to figure out what the distance is? We don't know how far they hiked. Okay, we're trying to figure out when they're going to meet, which is the distance that they've hiked, how long they've been hiking, but it doesn't tell us they hiked 2 miles. It just tells us the speed that they hiked, the rate at which they hiked, and the amount of time that they hiked. But remember, our distance formula tells us that the total distance traveled is equal to rate times time. And here we have rate, here we have time. So we're just going to simply multiply these two together. 5 times x is 5x for the total distance that the senior high class traveled. Now we can do the same thing. Rate times time for the junior high class. However, make sure that you put the parentheses around x plus 1. Because if you did not do that, if you just said 3 times x plus 1, you would have 3x plus 1. Whereas when you distribute this, this is actually 3x plus 3. Be careful to go ahead and make certain that whenever you have an expression that represents a single quantity that includes a variable, make sure that you use parentheses around that. Now, what we've done is we've filled out our chart here. Now, what are we going to be able to do? What do we know about distance? Let's look back at our problem and see what it says, because we have to come up with a formula. I mean, it's all well and good to draw a silly picture and a chart and fill in all the blocks, but if you can't come up with an equation to solve, then you really haven't accomplished a whole lot of anything. Well, it says, how much time will pass before the senior high class catches up with the junior high class? Like our illustration shows here, both of these two classes have traveled the same amount of same distance. Distances are equal. That means you can say the distance that the junior high class travels is the same as the distance that the senior high class travels. Now you have an equation that you can solve. We distribute and we have 3x plus 1. Haha, do we have 3x plus 1? Remember why I said to use parentheses? Because you have to distribute that. 3 times x is 3x plus 3 times 1 is 3 is equal to 5x. We want to isolate our variable on one side of the equation. I'm going to keep my variable on the right-hand side of the equation so that I have a positive. I don't have to worry about dealing with a negative number. If I want to eliminate the 3x on this side, this is positive 3x, what am I going to do? I'm going to subtract a 3x from both sides of the equation. 3x minus 3x plus 3 is equal to 5x minus 3x. In order to keep our equation in balance, you have to make sure that what you do to one side of the equation, you do to the other side of the equation. 3x minus 3x, 3. 5x minus 3x, 2x. It's all well and good to say that 3 is equal to 2x, but I don't care about 2x. What I'm solving for is x by itself, the amount of time the senior class hikes. Because I've multiplied x by 2, I need to divide x by 2. Do the same thing on both sides of the equation, and we see that x is equal to 3/2. Now this is a good example, perfect example here of what I've talked about, how you use improper fractions almost exclusively in algebra, unless you have a problem where it makes sense to go to a mixed number. So here we have x is equal to 3/2. But what you have to do with the word problem is you always have to identify what you have. You have to label. Is this 3/2 of an orange? Well, no. X is the amount of time the senior high class hikes in hours. So this is 3/2 hours. I don't know about you, but I don't go around walking in and talking to my kids and saying, okay, in 3/2 of an hour we're going to be downtown. We don't. 3/2 is 1.5. So your solution here for the senior class would be the senior class traveled 1.5 hours. So this is the example of the time that you do convert from an improper fraction to a mixed number because it makes sense for the problem. And this is exactly the way that your book chose to approach this problem. I'm going to set it up again in just a moment for you. Actually, kids, what I'm going to do is have this be part 1 of the video so that you don't have a monster-long video out there on YouTube. So you'll see the second half of this and possibly a third teaching segment on section 4.9.